All right, welcome everybody. So today we're going to talk a little bit about piecewise functions. The last video I did got corrupted, so it didn't really work, and I didn't have time to fix it before. But let's talk about it anyway. So this is a function, and it's just a different type of function. It's a piecewise function. All those are it really just says that if we want to have an equation to model some stuff, it depends on our input. Our input is our x. So it's going to look different from one x interval to another. Notice how it looks different from here to here. Whoops. To here. And then it looks different from there to there and there to there. So there's a different definition for the function. There's 3 different pieces of it, and we can write it a lot of different ways. So we can evaluate these graphically or algebraically. And these we're going to do graphically, and at the end we're going to do algebraically. So the function f is graphed below. Determine the intervals on which f is increasing or decreasing. Let's just remember something. When we're talking about increasing or decreasing on a graph, what we mean is as we go left to right, what does our y do? As we increase our x, what does our y do? And what I mean by that is we only really look at these things left to right. And Mrs. Zenos likes to to imagine there's this person on it that's walking, and we'll call him Bob. And he can only walk left to right. He can only walk right. And we're going to kind of look at the slope of if he's going up a hill or down a hill. So on segment 1, as he walks down a hill, if he walks from left to right, he's walking down a hill. So this one is decreasing from this interval. On this interval, it is decreasing. Now Bob is walking to school from left to right still, and suddenly he looks like he's going up a hill. So on this interval, it's increasing. And last but not least, Bob is walking on that hill. Somehow he got taller. And on this interval, it is also increasing. And that's all you really have to think about. As you go left to right, what is your y doing? Is your y getting bigger? Then it's increasing. So just look at it from left to right and you're good. So segment 1 looks like it's decreasing. So we'd put this function is decreasing on the interval from -6 to -1. We like to start with our lower number when it's written like this, just remembering how inequalities work. So -6 to -1. And again, just make sure that your signs that your inequality symbols are correct. This is a compound inequality, also known as an interval. So in this case right here, we can look at it one at a time. Whatever x's we care about, they are stuck between -6 and -1. But if you look at a compound inequality as one inequality at a time, you can see that the big part of the inequality symbol is facing the x. That means that x is greater than -6. So it's to the right on the number line. It's to the right of -6. And you can look at it as x is less than -1. So x is greater than -6 and less than -1. So it's basically the intersection of 2 different inequalities. That's what's happening here. Now, just as a reminder of interval notation, just in case you like it, you can write this in interval notation, which sometimes looks like a point, but it's not. You'd say on the interval, and then you'd give the interval. So it goes from -6 to -1, and interval notation, if it is equal to that number at the end, it's a square bracket that looks like this. If it is not equal, so something like that. So this is if it can equal those points, or if it has a closed dot at those points, and this is if it can't equal. So in this case, we'd put on both sides, we'd put an open set of parentheses like that because this does not equal. It's an open dot. This also does not equal. It is an open dot. But either way, that's just some little nice interval notation reminders. but we can also just use it as an inequality. Now, on segment 2, it looks like from left to right, it's going uphill, so it's increasing from, well, this right here to this. So -1 to 3. It's really about just looking at the left endpoint and the right endpoint. Just looking at the x values. That's what we care about. So you can just kind of drop that point down to the x-axis if you want to figure it out. And lastly, segment 3 looks like it's going uphill, just less uphill, but it looks like it's going uphill. So it is also increasing. And its interval is from 3 to 9. And that's all there really is to these. Same thing here. Looking at this interval of x's, we only care about where it changes. It looks like going left to right, it's going downhill, so it's decreasing from -9 to -3. And again, just double check your inequality symbols to make sure you're plugging it into the right spot. Again, looking at this, it's saying that x is stuck between, it's like the sandwich or a s'mores. X is stuck between -9 and -3, so you can look at each part individually if you want to do a sanity check to make sure that you're not messing it up. X is greater than -9, and x is less than -3. That's how you know it's stuck in between there. All of your x values, remember with your graphs, it's just an infinite, when it's continuous like this, it's an infinite number of points, all with x and y values. So when it's continuous, all of the x values in between are represented. There's an infinite number of those. So we don't want to just write whole numbers. That's why we have to use this interval. It says all of the x's from -9 to -3. If x is -8, we're good. If x is -7.5, it's in there. If x is -7.5, it's like right in here. If x is -5.0001, it's like right here. All of those numbers are included. Now, segment 2, it looks like it's going up again, so it's increasing from left to right, from -3 to +2. And then lastly, segment 3 looks like it's decreasing as you go left to right, going lower from 2 to 8. So it looks like it's decreasing from 2 to 8. That's all there really is to that. Now we want to learn how to evaluate these things. So f of -3. Let's just remember our function notation real fast. This whole thing stands for our output. F of -3. When we plug in -3, if we have an algebraic equation or when we look at a graph, we care about the y value, the output value. That's all this represents. And the part that's inside these parentheses, that little argument, that is not multiplying. It is saying that that is the input of the function. That is our x value. So in our case, that's what we know. We want to give the y value when the x value is -3. That's what it's looking for. That's all this means. So when x is -3, here is a fancy line. That is the line x equals -3. Every single place on that line that I just drew has an x value of -3. And we want to look to see where it intersects our graph. But if you notice, it doesn't. It does not intersect our graph, which means that our graph is not defined there. That's the only time you should hit undefined, is if your graph is not represented where you're looking at it. Now, this would be a completely different answer if we had been asked a different question, as is the normal. If we had instead been asked, what is f of -5? If we had instead been asked, what is f of -5? Well, drawing the line, usually we just do this mentally, but you can always do it. Drawing the line, x equals -5, notice on that line, every single value, every single point on that line has a value of -5 for x. So right here, this is x equals -5, y equals 9. This is x equals -5, y equals 6. This is x equals -5, y equals 3, and so on. But the idea behind this, the logic behind this, is to see where it intersects our graph. It looks like it intersects right there at the point x equals -5, y equals 3. But this thing just wants the y value because that is the output. Basically, f of -5 equals 3. You can write it like that, but it's just looking for you to put 3 right there. Now it says open and close dot business that messes students up a lot. So this is looking for f of -5, and if I draw this line right here, where x equals -5, everywhere on that line x equals -5, we need to figure out where it hits our graph. Now this can look confusing because you've got an open dot right there, an open dot right there, and a closed dot right there. It looks like it hits it in 3 spots. But the definition of an open dot just means not equal. That point does not exist right there. It does everywhere to the left, so as you approach it, like -5, just x equals -5.1. That would be right here on this part. There is a point that has that. X equals -4.9. That'd be right here. It does hit it right there. But at x equals -5, you've got a bunch of open dots, which means that it doesn't equal right here, so it's not going to be that. Right here, so it's not going to be that. The only point that is a closed dot is that y equals -3, because the closed dot is the only time a point is equal. So if your endpoint has a closed dot, it means that it is equal there. So in our case, the only thing that we actually care about is this: when x is -5, y equals -3. And what's interesting about this, sometimes they give you this and they make it a little confusing. They might say something like, what is f of -4? But then they have open and closed dots, so a lot of students think, oh, I better put the closed dot. No, that only matters if you're right there. So right here, this is the line x equals -4. This is where it hits the thing, y equals 0 there. Just make sure that you're doing little sanity checks for that. And lastly, for our piecewise functions, we're going to do 2 things where we try to plug them in. So it works the same way for an algebraic expression. Our normal functions, as we saw them, looked like this. It was just something like this, x squared plus 5x plus 1, something like that, or other things. And they just had one definition. That meant that for all real numbers that are in the domain, plug them in. You don't have to think. But a piecewise function, it has multiple different pieces depending on what your x is. And this is how we notate it. This is saying when x is less than -3, plug that x in here. Or when x is equal to -3, plug it in right here. But there's nowhere to plug it in, so it's always -1 there. And this one is saying when x is greater than -3, plug it in right here. That's all. So when we're trying to find f of -1, we need to figure out where to plug it in. Students mess this up a lot because of the fact that they, are negatives and understanding less than a negative number. So f of -1. I'm going to tell you, plug it in right here. Remember, if you were to draw your number line, there's no shame in drawing a number line if you need to. And if I were to actually draw each one of these points, if I were to draw each one of these intervals, let's do this one in red, let's do this one in blue, and let's do this one in green, a better green. So on my number line, if I were to graph x equals is less than -3, it's not equal, so it's going to be an open dot. And all of the values to the left are less than. That's the part we need to remember when it comes down to less than. It's just going to the left. And then for this part right here, x equals -3, that's going to be a closed dot at that point. And then there's a green one. When x is greater than -3, it'll basically be an open dot with the green right there and everything to the right. And that's it. So when we want to plug in these things, we really just look at where that is. We're looking for f of -1. When x is -1, well, that's right here. So it's going to be on that green branch. That's how we can figure it out. Sometimes that can help us figure it out. When you get good at it, you don't really need the number line anymore, but there's no shame in using the number line to remind yourself. Like, you can draw all the intervals themselves and then just put your what your x value is in your function. This is saying x equals -1. What is the function spit out? And that's how you can know where to plug it in. But if you're good at plugging it into the correct one, then you just have to understand. Plug it into this one. So I get -2 times -1 minus 1. F of -1 is that. You just plug it in. And then I get -2 times -1 is +2. Everything else stays the same. 2 minus 1 is 1. So our final answer would be 1 in this case. If I wanted to plug in x equals -5, I would plug it in right here. If I wanted to figure out f of -3, I'd plug it in right here because it's the only one that can equal it. If I want to figure out f of 17, it goes right here because that's the only one that counts x as greater than -3. That's to the right of the number line, so 17 qualifies. Anything, really. F of -1,000 would go into this one because that's less than -3. And for this one, find f of -1. I need to figure out what interval it goes in. Now, here's the thing. When I look at this interval, this is all of the x values between -5 and -1, including -5. That's what that little equal sign means when right here. It means that x is greater than or equal to -5. This one doesn't have that or equals. So when we're looking to plug in -1 somewhere, we look at this and we're like, no, there's an open dot there. Man, x is less than -1. That can't go into that branch. So you might be tempted just to go ahead and plug it into the other one, but look at that other one. Notice, on this part right here, x is just strictly greater than -1. It doesn't equal -1. So again, open dot right there. So what's weird about this whole thing, it doesn't look like it's defined at all for x equals -1. So that's where you'd go undefined.